Okay, so in this case, you should say that that is pretty much equal to P, which is the true proportion. Now, this one was interesting here. If the population proportion changed to a 0.5, what would the new mean be? 0.5. Okay? And the reason is the P hat is your best estimator for the proportion. Okay? That's what you're doing with the statistics. You're gathering a small sample to make decisions based for the entire population. So if your sample gave you a P hat of 0.5, then that P hat is the best estimator for the population parameter. Okay? Yes, we understand that if we got a different sample, that number would be different. Okay? But later on we'll discuss about that margin of error. Okay? But for now, you need to understand that P hat is your best estimator for P, and X bar is going to be your best estimator for your mu. Okay? When we start talking about the margins of error, then you'll see what's going on with that. But that's the best shot that you've got. Okay? You understand that? Yeah. Now, it seems like people still don't have a grasp of what this sampling distribution is. Okay? It kind of people understand it, but you kind of don't. So I want to try something a little different. Okay? So everyone understanding here, we have like what, 35 bodies in here? Okay? You guys are in the population. Let's pretend that you guys are all of the teens that existed in life. Okay, and this is it right here, the 35 of you guys. I don't know if there's really 35, but I'm going to say there's 35 of you guys. Okay, and I want to know, because I want to buy a couple of druid hoods and cape stuff. I don't know. So I wanted to find an average height so that they all kind of fit everybody. Okay? But I don't know. This is the first thing that came to me. So maybe I want to buy a pair of shoes that everybody can use a couple of times. I don't know, whatever. But I don't want to deal with all 35 of you. Okay? I just want a small sample because I can grab a couple of you guys, right? Okay? So there's 35 of you guys, and I could say, you know what? I'm going to randomly pick 5, and it could turn out that it's these first 5 here, right? Or it could be that would be one mean, wouldn't it? Okay, so let's say by some chance I got these first 5. That's going to produce for me, on the number line, some average. And I'm like, okay, that's the average shoe size. I think those 5 can wear that shoe. Okay? Now, it could turn out that it was these 5 here. Right? But that would be a totally different number, wouldn't it? Okay? That would produce a very different, probably a smaller X bar. Okay? Or maybe it turns out that I got the 4 back there, including Spencer, and then Jose. Right? That would produce another X bar. How many of these X bars could I produce from this 35, this N equals 35, this population of 35 people? How many different X bars can I make? A lot. Well, that is technically, do you guys remember when we did the binomial coefficient? When we said, hey, what's the probability of this happening? And we said, oh, that's a probability, but it can happen a bunch of different ways, couldn't it? And we did N choose K. Well, same idea. 35 choose 5. Okay? So let's figure out, I'm going to use a calculator. Is that 30? How many different ways? Did I just hear someone say something? 35 math probability choose 5. You guys ready for this number? How many different ways did you guys say? Did you guys guess?
Wait.
There are just from these 35, if I chose you 5 at a time, I can get that was just a little bit off. I can get 324,602 different X bars. That's how many X bars I would have. 324,632 that would make up this thing called a sampling distribution. Deja, how many different samples can I get? A lot. Okay? And that doesn't feel that way, does it? There's only 35 of you guys. But you know what would turn out is that this would have a somewhat normal shape. And we like normal because we have tools for that. we have that Z chart. You guys remember that? Okay, so why are we even doing sampling distributions, right? Don't we already have raw data? Well, the thing is that raw data doesn't always look nice. And that's the truth. Okay, if we take a look at even our scores for some of the tests that we've taken, a lot of them are skewed. Okay? Our distributions would look like that. Or sometimes you have some, that we get a lot of D's and maybe a lot of C's, which would make the distribution bimodal. Okay, because we probably don't have a lot of F's, we probably don't have a lot of A's. So the thing is, how do we work with that memo? And that idea is a sampling distribution. If our sample size is large enough, then when we produce the sampling distribution, then we're going to get a distribution that's normal. And then now we have those tools to work with again. Understand? So that's what we're working with. That's the idea right now, is these things called sampling distributions. Let me clean that up.
Jackie has a question, sir.
Jake, call in.
I don't understand why, the question just says what is the mean of the distribution, but the answer was P hat. P is not.
Yeah, and it's called a mean. It really is. Take a look at your formula sheet. Because what is a mean? Think about it. What is a mean? Isn't it the center? It's the center, right? So if we're looking at the center of a p hat, we could still call it the mean, but understand its proportion. It's a different type of data. Okay, and that's how we differentiate between the two. So whenever I say, because there's going to be two of them that you're going to see. You're going to see the mean of p hats, and you're going to see the mean of x bars. Okay, what type of data am I working with here?
Oh, statistics.
What type of data? What category of data? Sorry, not what category of data. It's either going to be qualitative or quantitative, right? So when I see this is telling me that it's going to be quantitative. Okay? Now, here's the deal, Jacqueline. Why are we using this symbol for a p hat, right? That's what you're kind of asking me? Right, because isn't mu mean?
Yeah.
Right, so what is our Z table or Z chart composed of? What's it look like? That, remember? And if we wanted to find a Z score, what did we need? Didn't we need a mean? We would take a mean, so we would go, it would be x bar minus x, and then we divide that by the standard deviation, and that will produce a Z score, correct? We want to use all those tools because that's what we got good at the first semester, or should have gotten good at, okay? So what we're trying to do is trying to make all this other data fit those tools. So that's what we call this. If we're trying to find a mean so that we can use it here, then the best way to do that is simply that. Okay, so the mean of your p proportions is going to be p. And so it's just kind of saying, you know what? You can take this number and it would go there.
I thought proportion does not mean what should happen. I thought this was
Well, yeah, that would be p. That's what you want to happen. But p is simply a category type data. So if I was going to say, oh, you know what? I want to know how many people lick the spoon, from peanut butter and they dip it back in the peanut butter. You know that gross thing that people do? Double dipping. Thank you. Double dipping. How many people double dip? Okay. And then I could find the proportion of double dippers. Okay. According to that, that's what I'm interested in, right? It's double dippers. Or maybe I'm interested in people that aren't double dippers. Then that would be the title that's assigned to P. It's what I'm looking for. It's my parameter of interest. Okay. Does that make sense? P is going to be called exactly what we're interested in. Okay. Am I interested in all people that eat peanut butter? No. Technically that would be the population, wouldn't it? Okay. But the parameter of interest is how many of those people are double dippers. Make sense? Okay. And the sample would be considered the people that I picked.
So say
Is that making sense?
They would not
I wouldn't care about those people because would they eat peanut butter? No. The population would be all people that eat peanut butter. Okay? And guys, to try to lower the number of mistakes here, there's only two things that you can ever say for a parameter of interest. What are those two things? Do you guys remember?
Surely.
For a parameter. If I'm looking for a parameter, there's only two things that I can say. And it should all start with true. I'm looking for the true mean or the true proportion. That's it. There are no other options. Okay? Well, for here, what they're saying is if I've got the sampling of p hats, what is going to be the mean of that? Well, if I'm working with p hats, well, p hat is the best estimator that I've got. That is going to be equal to the true proportion. Yes. I know it's a funky word, and I really don't like the way they use it, but that's not my rules. Okay, because it really does mess with me, because I'm thinking I'm back with quantitative data. But it's not. It's simply a rule to kind of get me back into this mode where I can use my standard deviation. Okay? But truly what's going to happen is this formula will change. Okay? This formula will change once we get into sampling distributions. And here's what they'll say now. And it's kind of the same idea, but what they'll say is a parameter minus a statistic, and then you're going to divide that by the standard deviation of that statistic. Okay? If you look at your formula sheet, they've changed it now so that it makes a little bit more sense. Okay? It's still kind of the same idea, isn't it? I've got some kind of parameter, which is x bar. I'm subtracting from that some statistic, which in this case would have been the raw data, and I would divide by standard deviation. Okay? What's going to happen here is that we're going to get two options. Go ahead and grab your formula sheets if you have those. Yeah?
Parameter minus statistic over
Standard deviation of that statistic.
standard deviation of that statistic.
Yeah, standard deviation of the stat. And it's the formula's on your formula sheet, it's at the very top. It's the first one, I believe. Okay. No. If the population proportion changed to this, because here? That's just a given. That's the rule. That's your best estimator. Yeah, you just need to know that. What's the best estimator for mu? Your x bar. Exactly. Okay, that's the best I could do. I don't have anything better than that. As long as my sample came from an SRS. Does that make sense? Like if I had a sample size of 1,000, but I picked them, is that x bar a good estimator from you? No, because there's bias involved. Does that make sense? Which is actually a great setup. Thanks for like kind of setting me up there because remember the ultimate goal is to try to use normal tools, right? Okay, so normal tools because I want to be able to use that Z chart. Okay, but there's some things that we all know that need to happen. One, the distribution has to have what shape? It has to have a normal shape, right? So can everybody agree that that's one of the conditions that we must have in order to use the Z chart? Cool. Okay, now let's talk about what you just said. If we have an x bar, I have to make sure that that x bar is a genuine x bar, right? That means that my sample must be unbiased. So we have to ask ourselves, hey, you know what? Is there bias involved here? Is this distribution normal? And then there's another thing that we're going to talk about, which is independence. Okay? Okay? Independence. This sample of 35 people is kind of small, isn't it? Okay? And even within the school, what one person thinks influences a couple of them, doesn't it? Everyone agree with that? So if my sample size is small, then there's more chances for that influence to happen, isn't there? So I want independence. And in order to gain independence, what has to happen with that sample size? It has to be what? It has to be bigger because then there's less chance for that adulteration, I guess, of opinions. Does that make sense? So larger sample size guarantees me that I'm going to have some independence there, okay? That's some great questions, Jacqueline. That was really amazing. Thank you.
Before you go to that, can you go over the homework, please?
Oh, 11? You weren't supposed to do. So I believe it was 11,
So I tried
9, 11, and 13.
Okay, I wish I didn't know.
Okay, I think I said everybody, you know what? It says use Fathom software.
Yeah, and I didn't know what that was. I
You
just like
don't have Fathom software.
I
Okay?
didn't know what to do.
It's like if I told you, hey, you're playing basketball, go make me a touchdown. What? No, you're fine. You're fine. That's my fault. I just grabbed JP. I just grabbed the recommended problems and I give them to you.
Okay.
What's recommended you guys do? Obviously, they're not all of them either. It's just a sample of them. So, and I don't filter them. All right, cool. So, shall we continue?
Ignore the gibberish then.
Let's shall. What's that? What's that? Here we go. Okay. So, hopefully this will start making a little bit more sense. Again, we're dealing with this thing called sampling distribution. Main reason is we don't know if all data is normal. Okay, we're going to be dealing with different types of things. One of them being that now we're going to also be working with proportions, right? So that's the first one we're going to talk about is proportions. So we're looking at the sampling of proportions. Let's take a look at this problem first. A Gallup poll found that 210 out of a random sample of 501 American teens aged 13 to 17 knew the answer to this question. And the question was, what year did Columbus discover America?
1492.
Okay.
Right? 1492.
I don't even know it. Is it 1492? Yeah, no, 1492, Columbus sailed the something blue. Ocean blue, okay. So we have this, let's interpret that, okay? Let's take a look at some questions here. For starters, what is this number here?
Mean? Average?
It is the p-hat, okay? It's the statistic. It's the statistic. How do I know it's the statistic? They took a sample of 501 Americans, okay?
So P-hat's always. I'm not connected.
Well, in this case, hold on. Well, let me ask you this question. You want to figure out whether it's a mean or if it's a portion, right? First, well, look at the type of data I'm working with. Is it categorical in nature or is it quantitative in nature? Yeah, because what am I asking them? Hey, do you know? So either you fall into the I know or the I don't know. Make sense? So let's talk about all those things real quick. Let's start with the population. Okay, who's the population of interest here? American teens that are aged 13 to 17. That's my population of interest. Okay? What's the other question they would ask next? What's the parameter of interest?
501 American teens.
The parameter of interest. What am I interested in knowing?
Oh, 210.
The proportion of these students that knew the answer to this. Okay? That's my parameter of interest. Okay? It's the proportion of the teens that actually knew the answer. Okay? And then you have the question is, what's the sample? Well, what was my sample? 501. And what's my statistic?
0.42.
It's the 0.42. It's this number, because that's the one that knew, divided by this number. And that's all the numbers that you need to know. Okay, so there it is. This is a p-hat. So, is 0.42 the parameter or is it the statistic?
Statistic.
So, here's the next question. Does that mean that only 42% of American teens know this fact?
No.
Yes. Yes, you said it. What would you say first? Close. Okay? But this is the best guess. What?
He said false. What is it?
False. That is I can safely assume that 42% of all American teens know it. Okay? Say that again? Yes, thank you. Yeah. So I can safely assume that all American teens aged 13 to 17, that only 42% of know that Columbus sailed the ocean blue in 1942. 1942.
1492.
I was on the Mayflower, people. What? It is a statistic, but it's the best statistic I have to make conclusions about the population. Does that make sense? Cool. So, Aaron, cool with that? Question, what's the proper notation for this statistic? P hat equals 0.42. Can you leave it as a fraction? You can, but you want to go with the decimal. You want to go with the decimal.
What is P? Just P equal. What does that mean?
It would still be 0.42.
It's still.
Yeah, because here's what you found. Based off of this sample, I found that the proportion of people that knew was 0.4. They're horrible. 0.42. However, that's the best that I have. Therefore, I'm going to make the assumption that 42% of the population knows that. Okay?
Wouldn't you do like the squiggly?
No, we would make it the assumption because it was an SRS, which means that it's not a biased, there's no bias involved in that number, therefore it's going to give me a true representation of what's really going on. Okay? That makes sense? We're good? Cool, cool, cool. All right, moving on. Write these down, please.
Yes, sir. In our notes or on the sheet?
Actually, you have these, I believe. Let me check on your format sheets. You should have those. Okay. So remember we wanted to use the Z distribution, right? That normal distribution chart to get Z scores and probabilities and all that good stuff. But in order to do those, we need a mean and we need a standard deviation. So if I want to find the mean of a p-hat proportion, they're on there, good. Then that's simply going to be P. If I want to find a standard deviation of this p-hat, okay, and these formulas should look familiar. Aren't they just some rendition of what we did with probability? Yeah? So here we go. It's going to be root PQ over N. That's the one I like because it's shorter. It's simply the probability of success multiplied by the probability of failure divided by my total sample size. And I take the square root of that number.
What's the probability of success?
It's the number of successes multiplied by the failures and then divide by my sample size and they take the square root of that whole number.
Probability of success times the probability of loss or probability of failure.
Yeah, it's successes, failures, and the whole thing.
The probability of the actual answer.
Well, so like in this last problem, what's P? It was 0.41, wasn't it? Was it 42? Okay, so 0.42. So what would Q be? 0.58. And then sample size? 501. So do that, and then take the square root of the number, and you got your standard deviation. Okay?
I know, yeah, that's what I'm like, I get this right now, and I'm gonna go to homework tonight, and I'm gonna be like,
But here's the catch, though, people. Here's the catch. There's got to be a catch, right? This is okay. That's my best estimator. But for a standard deviation, you guys remember how when we first learned about standard deviation? It had to do with the normal distribution, didn't it? So that means that in order for me to be even able to use this, I need to be able to have, I have to be able to have an unbiased statistic. And how does that happen?
SRS.
That's bias.
Lots of numbers.
SRS is bias?
Okay, so if I'm going to have independence, then I should have no what? I should have no bias, right?
Yeah.
So we want to make sure that there's bias. First identify, is there bias here or not? And how do we say if there's bias or not? How can I determine from this last problem there was bias involved? Wrong way. Was there bias involved in this problem?
It's random.
Exactly, that's it. That's all you can say.
Random.
Is there bias? You would say no, because this was a simple random sample. Okay? Remember, simple random samples assure that you're not going to get, well, you're going to reduce bias. Will you ever eliminate it?
No.
No. Skylar. Good. Okay. Now, the other thing you could probably say, if this was from an experiment, this was a well-designed experiment. Because if it was a well-designed experiment, then surely they used an SRS. And hopefully. Now, SRS is probably the safest bet. Okay? If you're talking about experiment, read the experiment and see if all people were assigned through an SRS. That's my key thing. Every time I'm going to look, I'm going to say, I'm going to look for SRS. Was this an SRS? If they use an SRS. SRS, SRS, SRS. That should be the only answer. If you don't find SRS in there, you can't. Okay, because, and I know what you, I would, if this was real life, I'm like, you know what, these results, So what I'm going to say is, you know what, once you check for bias, and you could not confirm that this was an SRS, then you should say, proceed with caution. There is no evidence that an SRS was used. Make sense? Because if you're taking your AP test, and you just say, oh, you know what, there's no SRS, I'm not doing it anymore, guess what? You're fooled. You're wrong. You just lost the points. Okay? So always just say, proceed with caution. There's no evidence to suggest that an SRS was used. Okay? Now, we've established that there's no bias. The other way to reduce bias is to have, remember what I said about the small groups?
Larger sample sizes.
So I need to have a large sample. So in order to have large sample sizes, I want to make sure that I have independence. Independence. Okay? So independence can be gained from, okay, actually here they are, right here. From large sample sizes. Okay? No slow claps. Okay, I'm not even done yet. Your guarantee for independence. You want to make sure that that the population is really, really large. So what you're going to do, Tangelo, is you're going to multiply your sample size by 10. Okay, so you're going to take, you want to make sure that your sample size, so 10 times your sample size is that your population, so capital N, your population size is going to be greater than 10 times the sample size. So for example, in the students one, what was it? How many kids were there? It was 501. So I want to make sure that the population, come on. Population is greater than 501 multiplied by 10. So guys, do you think that there is more than 5,010 teenagers aged 13 to 17 out there?
Yes.
Yeah. Okay. So definitely that means that because the population is so large, this sample is independent. Everyone got that?
Yeah.
Okay. Now, if that wasn't true, this statement wasn't true, what do you say? How would you respond to that condition? PWC. Proceed with caution. Seems the population is too small. It was very small or something like that. Okay. Seems like we got a small sample or small population here. Okay. Okay. Now, one more condition. I need the shape to be, what type of shape? Normal. Okay? I need it to be normal. That means, in order for my distribution to be normal, it's got to be half one side, half the other side, correct? Kind of thing? That idea? Which means that you need to have at least 10 successes and at least 10 failures. So let me say that one more time. And let me see my notation here. Okay? So to figure that out, you're going to take your sample size, multiply by P, and make sure that that number is greater than or equal to 10. This gives you the number of successes. If you take N and you multiply it by Q, that number should also be greater than or equal to 10. So if we're looking at our teens that are aged 13 to 17, 501 multiplied by, what was the success number? 442? How much is that? What's 42% of 501? It's more than 10. I know that, but we'll say 210? Sure. Now, 501 multiplied by the point, what is it, 58?
Yeah.
Is this number greater than or equal to 10? So 93, 91? Yeah? Oh yeah, 291. Thank you. What am I doing? Okay, so there's my math. I've shown that the number of successes is greater than 10 and the number of failures is greater than 10. That's going to assure that my distribution is going to be normal. Do not do this, because I see that a lot of people do this. They'll go NP greater than 10, and then they'll check on the calculator, and they go, yep. And then they go, oh, the number of failures is greater than or equal to 10? Yep, and they do that. Check mark, check mark. You fools. You'd be wrong. You just lost points. Okay? Do the math, and then show them. And then you're going to, some narrative down here. Because the number of successes is greater, number of success and failures is greater than 10, then we can safely assume that this distribution will be normal, or the sampling distribution will be approximately normal. Do we say it's going to be normal? No, we say approximately normal. Okay? Questions on that? So, we have three conditions. I want to go over them again. I think I got a slide here. Okay, so three conditions. And the way I remember those three conditions is with bin. It's with bin, B-I-N. What's the B for? Not binomial distribution. This is just bin. To remember the three rules the three conditions I must meet in order to use my normal tools. Okay? So, is there bias? Is the first one. What's the only way I should be answering that?
A little bit.
What's the only way I should be answering is there bias?
No. Always very little. It's always going to be very little bias.
Did your data come from an SRS? If it's an SRS, then you're going to say, yeah. They clearly state that they did a simple random sample of blah, 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 blah. So then you would be good. Don't go, is there bias? Oh, no, it's good. Check. Why? You just lost points. You fools. What do I need to check for next? Independence. Okay? Independence. How do I check for independence? Huh?
Size of the sample.
Size of the sample has to be larger. Sorry. The population has to be larger than 10 times the sample. So, my population has to be greater than or equal to 10 times my sample. And notice the notation again, okay? Lowercase n, capital N. Capital N denoting the population value, while small n would be the sample number, okay? How do I test for normality here? Because that's the other one, right? It's the shape. I got to make sure it's normal. Correct. I need to have at least 10 successes and at least everything is erasing on me. And at least 10 successes and 10 failures. Okay? And sometimes it's going to be very clear to you that, hey, you know what? There's no way this number is definitely going to be greater than 10. But still write the number down. Don't check mark it. You'll lose points there. J-Dub? Okay? So there's the three conditions that you need to make sure that you meet before you can even attempt to use your normal tools. Okay? Yeah.
Just years, like the past couple of years, it's been raining a lot.
I don't know. I haven't noticed.
What?
I like the rain, so I'm not like.
I never said I didn't. I'm just saying.
You've noticed more. That's true. He didn't say that.
He's getting really defensive here.
I don't like your attitude, sir.
I don't like
All right, cool. Oh, so let's see. Okay, so here's our rules of thumb. Draw distribution. Let's see your different question. Okay, let's try this one real quick. You guys ready? An SRS of 1,500 first-year college students were asked whether they applied for admission to any other college. In fact, 35% of all first-year students applied to colleges beside the one that they were attending. Here's the question now, guys. So now we're actually working with this distribution. You guys ready? So what is the probability that the poll will be within 2 percentage points of the true P? See how now it's getting a little bit more interest on her? Okay. So an SRS of 1,500 first-year college students were asked whether they applied for admission to any other college. In fact, 35% of all first-year students applied to colleges besides the one that they were attending. And then the question is, what is the probability that the poll will be within 2 percentage points of the true P? Okay. Now, do you guys see how within kind of goes back to when we were working with the normal distribution? Oh, you know, what is the what proportion of the population was within one standard deviation of this? That's the idea. That's what we're trying to do. We want to go back and we want to use those tools that we had from the very beginning because they were easy to work with. Here's what I know so far. Because they gave me a p-hat, that has to be equivalent to the true mean. of 0.35.
Can you go back really quick? I'm sorry.
Did you just go in the tree?
No.
Okay. JK.
Okay.
JK, hello, smart face. Don't look so sad. Life keeps on turning.
I'm trying, so it's not working.
Okay. Can I move from this slide for you?
Yeah, go ahead. I got
Okay, cool. So, everyone agreed this part. For starters, we're trying to find the mean because we're trying to use these old normal tools that we had. Right, Tanjo? I see you focusing, man. Struggling. Stand up a little bit. It might help. Okay? So, we have a mean now, which is 0.35. We need a standard deviation. So, here it is, 0.35. Right? That was the P. That means that Q would be 65. Okay, you want to check it? What should they both add up to? They should always add up to 100. And then we're dividing by 1500. Why? Because that was the sample size that we had. Okay? So that produces this 0.01 standard deviation. Okay? So now the question is, what is the probability that the pole will fall within 1% of the true proportion? So here we go. Do you guys recognize this? That was the z-score, wasn't it? What is this first number representing? I think I wrote it backwards. So take a look at your formulas. Yeah, I did. The first time that I wrote it, I think your notes are wrong. I think I said parameter minus statistic. It should have been statistic minus parameter. Okay, so double check. It's on your formula sheet. I just checked it right now, and I think I said it wrong.
So you switch these
Okay?
over?
You remind me to get your formula sheet. Or you should have some notes from, no? JK. So if you take a look at the back under the third block, it's at the very top, and it says statistic minus a parameter divided by the standard deviation of that tangelo. Okay, of that statistic. So here's my statistic. Here's the very top, the very top.
I know, it's a statistic.
Okay, yeah, so it's a statistic. Good. So here's my statistic. That's the parameter. And then we're dividing by the standard deviation of that statistic.
Yeah.
Oh, but it's going to be 2% off.
But what if it's 2% like points?
You have to check both ways.
Yeah, what were we asking for? Within 2 percentage points, right? So, isn't 0.33? Thank you. Oh, he's not here.
Is that here?
Yeah, I think he dropped the course.
Okay.
Okay? Shut up, yo. He told someone I threw him out.
Yeah.
I didn't throw him out.
I saw you do it.
I can't pick up that boy. Nah. For his own benefit, he should not have stayed. Let's just say that. Okay? So 2 percentage points. That means that I'm going to have a z-score of negative 1.626. Now, obviously, you guys already know what the other part's going to be, right? Because that's 2 percentage points below the mean. The other one's going to be 2 percentage points above, so it's going to give me a positive value. So now we're using those normal tools, aren't we? We're going saying, hey, you know what? The true mean is supposed to be a 0.35. I want to know what it is if I went from 0.33 to a 0.37. So I'm looking for the area in here because that would be the probability of falling within those 2 percentage points of the true mean. Coming back to me.
Wait, don't move.
The formula sheet's on the campus or online or
So,
something?
okay,
Yes.
right before this, you were talking about like a BIN,
Yeah,
and then now we're doing this, and how can you tell what you're supposed to do?
you do it all. Here's the thing. Here's the thing. The data you're working with are proportions. Okay? Did we have, at the very beginning when we were doing this, did we use proportions here? It was all qualitative data, wasn't it? So we have to find a way to take this qualitative data and kind of use it in quantitative measures. In order to do that, we have to meet these guidelines, which was the BIN. One, I need to have a statistic that's not biased, because then that shows that I've got independence. And here's the deal, and I didn't say that. Once I've proven independence, that gives me permission to use this formula. I know this is the best estimator I've got, but what allows me to use this? And that's independence. Okay? Now, the other requirement we said is, man, you know what? That distribution we're going to work with has to take on that normal shape, don't we? And we assure that with the normality, having 10 successes and 10 failures. So following those three rules, BIN says, you know what? I know you've got data that's qualitative in nature, but because you met these three conditions, you're going to be able to use them using quantitative measures.
And then
So it's
we're trying to
qualities-
figure out the two numbers.
Say that one more time?
Like, since we're trying to figure out the two numbers, that's why we're using the Z.
Yeah, because we want to get these values so that we can actually create a z-score
So
thing.
bin is used to take qualitative stuff and make it quantitative. Is that what
So
you're saying?
if we would have
We
never.
want to take all data and be able to measure it in normal measures. Okay? Now here's the thing, guys. This is obviously not a z-score, is it? Okay? And if you notice your formula sheet, they don't call it a z-score. They call it a test statistic. Yeah?
What if we would have like not had something and would we say that it's not possible?
No, and that's what I said earlier. Let's say you were doing your three. I just lost the name.
Bin.
Yeah, from the bin. They're what do they call them? They're
Bias, independence, and normality.
no requirements.
Three
Conditions. Thank you. Let's say you're checking your three conditions, which is: do you have bias? Do you have independence? Do you have normality? If one of them you cannot assure it, you're gonna say PWC. Proceed with caution. Does that mean that you stop doing the math? No, you go through it, but at the end you just make sure that you repeat. One of the conditions was not met, therefore these results may be suspect. Proceed with caution. Because you've been hired to do the math. All you can say is, here's what you've got. Now here's the thing though. Later on you find out, hey, you know what? We didn't know if this distribution was normal, but now I've got more information and I can assure you that it is normal, therefore what I gave you is dependable. Does that make sense? So we still continue with the math, and then perhaps later on we'll get more information that confirms it. And I think you guys have seen that, right, with the frappies. There's one part, and then you kind of answer everything. You're like, oh, wait a minute, that was kind of the answer to part B, wasn't it? But they provide sometimes more information. So as you're doing these, you might get to a point and you say, proceed with caution. But then maybe at the end part C says, hey, you know what? John came back and said that we had, the distribution was normal to begin with. Oh, yay! Then all conditions were met and the data is reliable. Or, sorry, the results are reliable. Make sense? Good? All right, cool. So, going back to here, we did this. Now it's just a simple going back to your z-chart and figuring out what that area between a negative 0.628 and a positive 1.628 is. It turns out that this is what you're looking for. You're looking at the probability of a z-score between these two. Why? That is 2 percentage points within. 2 percentage points above, 2 percentage points below. Cool? Got it?
Sure.
Okay, that means that the probability of that happening is a,
Wait, where'd you get that?
what's the area of this?
Oh,
It's from my normal chart.
you said that.
So yeah, so what I did is I found here, let me see, I think I might have it on the next slide. Yeah, here it is. See, it's the point, oh, my bad. It's a 0.94, the area from this point all the way down, minus a 0.05, which is the area from this point all the way down, and that produced a 0.8968. So we can say about 90% of the samples fall within 2 percentage points. So would I be surprised if I did a survey and I said, hey, we found that the true mean was not 0.35 in this case, it was actually 0.34. Should I be surprised by that? No. Should I be surprised by if I got a 0.34, a 0.33, a 0.32? Maybe. But not really, because it's still what? I mean, that was only 90%. Can it happen if it's like 10% chance of that happening? Would you be okay with that? Okay. And remember, we talked about that fine red line, right? We'll talk about exactly how to pick that later on. And we say, I don't believe that one anymore. Okay? Questions here? Jim? Questions? Oh, sorry, Mr. Shapiro. Colleague of mine.
In texting, what is IDK?
I don't know.
Does anybody else know?
spit it out. That was good. Did your calculators work? Did you try one?
I didn't try the new set that you sent over.
Actually, I was more sure of the new set than the old set.
Right, the old set, there was a couple that I had problems with. Do I charge them turned on or turned off?
The little thing in the back?
Yeah,
On.
this is on and off.
On.
On.
On, because that's going to give it the battery supply.
And tell me, why did you give everyone back to me turned off?
Because I didn't want to go through and do that. I was lazy.
Well, see, now I assume that they're all supposed to be off.
Well, see, the deal was
Because 100% of what you just sent me.
they are all off.
Right.
Because here's what I had to do. I had to take that off. I had to take the cover off. I had to take the keypad off. I had to put in the old key or the Inspired keypad, update it, then go back and remove the keypad. Actually, take out the yeah.
Looking for a mariachi band to fill out your. Okay, so I'm gonna turn them all back on.
Yeah, just slide it. Just slide it to the on position, and then you can charge it that way. And we'll try to. I'm gonna try to see if I can buy the.
Why do they ever have an off button?
Because that actually turns on the navigator part, but it also kind of, I believe it lifts and makes the contact with the bottom of it. You know how it has that little drop door? So when you do that, I think it lifts and makes contact with the
Well, we had to turn them on in order to run the calculator.
Yeah. Should have two on buttons. Right?
One is the slide.
Yeah. And the other turns on the calculator. Alright. And I think they should work. I tried a few of them, and they came on just fine as 84s.
I had a couple of the black ones that didn't.
Yeah, okay. Send those back. And
I gotta,
I'll send
there's
some
5
later.
in the box, I gotta figure out which 5. Now it brings me up to 30, I'm still about 12 short.
okay, I'll send them with Lucino right now. Thank you. What's IDK? I don't know. Alright, cool. Let's take a look at another example. Thank you, folks. Yeah, right? It always gets me. I'm afraid to answer his questions sometimes. I'll tell you about the Chinese one. No, we got to get this lesson out. It's going to be way too long. So, another example. One way of checking the effect of undercoverage, non-response, and other sources of error in a sample survey is to compare the sample with known facts about the population. So, about 11% of American adults are black. Would you prefer African American? I've asked this question over and over because of this slide. I always ask, like, hey, do you prefer African American or black? I'm like, black. I ain't never been to Africa.
Yeah.
Except for you, you were born there, right?
My dad is from there.
Alright, cool. So, the proportion, the p hat, in the SRS should be about 11, correct? So if I know for a fact that 11% of American adults are black, then when I do a survey, what proportion of black people should I expect in my survey? 11, right? What if I told you I did one and I only got 9.2% black people in my survey? Would you call shenanigans? Would you say that's legit? Would you say that maybe there's some undercoverage going on here? What would you say?
If there's less, then obviously somebody wasn't responding.
So here's what we're saying. Right, so we're saying it's 11% of people, of all adults are black. That means that my SRS should also tell me that,
Nope, 11%.
okay, but I did a survey and I only got 9.2% people that are black.
But that's only 2 points.
It's only like 2 points, isn't it? So would you call shenanigans here? I don't know. We can run a test though, couldn't we?
Like if it's international, I feel like if it's American adults, like 2% of population like that will be like quite a few people.
Good
Just
point.
saying, like,
Good
and
point.
you're talking about
So wouldn't it be
millions.
nice to run some type of test to say, hey, you know what? You didn't do this correctly? So that's what we can do. Here we go. We know this, don't we? Right?
What is that first?
The mean of the p hat should be the same as the proportion. therefore it's 0.11. If I did my statistic for my standard deviation, that means I've got 0.11 times 0.89 divided by the 1500. That produces a standard deviation of 0.008. Say that one again?
Yeah, where'd the 15?
Where'd the 1500? Did I miss it?
Yeah.
I didn't see it.
Yeah, it doesn't say.
It doesn't say
Oh.
1500.
It doesn't say. That's how many people I sampled. I left it out. My bad. I left it out. But that's how many people were in our sample, okay? We're good? So, I'm going to find the z-score. Okay? Where does this 0.092 come from? That was my statistic, wasn't it? That's my statistic. Mallory, you got this done already? You already know how to do this? You want to finish up? Guys, you got to. This is easy. This really is some easy work. But if you don't listen to it, you don't hear it, you're going to miss it, and you're going to be hurting. And I'm not taking it easy on you guys. So, I don't know what to tell you. Focus. It's hard, I know. It's hard for me right now. I want to talk about other stuff. But anyways, moving on. This is a statistic that we have. We're testing it against the population parameter. We're dividing by the standard deviation of this statistic, aren't we? So that produces a negative. I told this guy I wanted to join, and he keeps calling me every day. They've got like this club thing going on. That's my statistic. Remember when I ran the survey? In my survey, I only had 9.1%.
That's
black people.
statistic minus parameter, all that kind of crap.
Statistic is not crap. Please don't call it that.
Statistic minus parameter.
You hurt my feelings. Okay. So here's what I've got. I got a negative 0.228. That means that I'm looking at for the probability that my z statistic is less than that. Now, what's the probability of that happening? So this is what it's saying. There's a 1% chance that that can happen. So even though it's only 2 percentage points, what'd you call shenanigans? Shenanigans.
How would you find that out?
We just did it. Go to your. I see what you're saying. Go to your normal distribution chart. Go to a negative 0.2228 and find that area right there. Okay. So yeah. So the fact that I only got 9.2%, that only happens 1% of the time. So I would say, sorry, sir, that's bull. Go ahead.
Oh, there it is. He just told like
Okay.
0.092. That was his.
We found that the z. Remember, we found a z-score of negative 0.228. So we go to our normal distribution chart, the z-score chart, and we look at what the probability of a z being less than negative 2.228. So distribution less than a negative 0.228, and then we find that area here. Okay? If you have your chart, find it, you're going to get that percentage. Okay? It's up to you. But what is it that we're after? If you round it up or down, are you still not going to get about 1%? You will. And that's what matters the most. Remember I said, we make decisions not with complete certainty. We want to make sure we do get the right answer at the end, though, right? Make the right conclusions.
So what's the line that you would say that it's not?
Well, for starters, we won't get there yet. But right now, let me ask you this. If I told you that that only happens 1% of the time, would you be okay with those results? No. I think we all agree on that right now. Okay. We'll talk about that fine line. It's called an alpha level. So we'll talk about it in the next few chapters. But right now, we want to make sure we get these bits down, okay? Right, Samurai? There you go.